Welcome to This Explainer. Grab a coffee, pull up a chair. Look, think of me as your senior engineer for the next few minutes, because today we really need to talk about keeping our APIs from totally melting down before your shiny new code hits production. We are talking about rate limiting, which is honestly the unsung hero of system stability.
So here is our game plan for today. Number 1, why rate limiting matters. Number 2, the core rate limiting algorithms. Number 3, scaling up to distributed systems. And finally, number 4, handling HTTP 429s gracefully. Let's get right into it.
Okay, part 1, why rate limiting matters. Let's dive in and talk about why we absolutely cannot let wild, unfiltered traffic just hammer our backend servers. Think about it for a second. What actually happens to a server when thousands of users suddenly hit our endpoints at the exact same millisecond? At its core, rate limiting is just controlling how many requests a client can make to your system in a given time window. But if we don't have that control in place, oh man, things get ugly really fast. It's exactly like a pressure valve on a water pipe. Seriously, imagine letting all the municipal water pressure rush into your house at once with absolutely zero regulation. The pipe bursts, the basement floods, the whole house is basically ruined. Well, your API is the exact same way. It is built to handle a very specific flow, not a literal tsunami. And without that pressure valve, the fallout is massive. First off, attackers, or just really poorly written bots, are going to drain our compute budget. We pay for the servers, and they just burn our money. Second, one flooded service cascades and takes down all the downstream services, wrecking the whole architecture. And third, you get that one noisy tenant in a multi-tenant system who just eats up all the resources, completely starving out every other legitimate user. So, bottom line, we have to protect the system. And our absolute best frontline defense is throwing the standard HTTP 429 status code, too many requests. When a client gets this, it's just the server throwing up a shield saying, whoa, hold on, I am at capacity right now, back off. Honestly, it's the cornerstone of any stable API. Moving to part 2, the core rate-limiting algorithms. Now that we know exactly why we need the dam, let's look at the mathematical blueprints for how we actually build it. There are 2 really common approaches here, the token bucket and the leaky bucket. Picture the token bucket literally filling up with tokens at a constant, steady rate. Every API request costs you 1 token. The genius of this one is that it totally allows for short bursts of traffic, as long as you have tokens saved up in the bucket. That makes it perfect for APIs where users might click around really quickly. Now, compare that to the strict pacing of the leaky bucket. In a leaky bucket, requests enter a queue and drip out at an absolutely fixed rate. Bursting? Strictly not allowed. It's awesome for smoothing out network traffic shaping, but, it can be a bit too rigid for normal web APIs. When you sit down to evaluate these major algorithms, you're constantly weighing memory trade-offs against burst handling. As a senior engineer, this is exactly how I decide what to build. Take a fixed window counter, for example. It's dead simple, uses almost zero memory, but the accuracy is pretty bad because of boundary attacks. A user can max out their limit right at the end of a minute and do it again at the exact start of the next, causing a massive traffic spike. On the flip side, that token bucket we just talked about, high accuracy, low memory, and excellent burst handling. There's a real reason heavy hitters like AWS API Gateway and Stripe use it. Okay, part 3, scaling to distributed systems. Because look, running these algorithms on a single local server is a piece of cake, but reality in modern cloud architectures, it is a lot messier. Here is the real nightmare scenario. What happens when your service scales up and runs on a massive distributed multi-node architecture? Let's say 100 servers sitting behind a load balancer. Keeping a global, real-time count of one user's requests across 100 different machines without grinding the whole system to a halt becomes incredibly tricky. Now, as a junior dev, your very first thought is probably, let's just use a centralized Redis database to count requests across all the nodes. And hey, it makes sense. It's super accurate. But watch out, because that introduces a massive bottleneck. You are suddenly adding an extra network hop to absolutely every single API request. And even worse, if that Redis instance goes down, boom, your entire rate-limiting defense breaks, and the system is sitting there totally unprotected. It is a terrifying single point of failure. The other idea people always pitch is sticky sessions, basically routing the same user to the same specific server every single time, so that local server can just keep the count in memory. Let me just warn you right now, doing that entirely defeats the purpose of dynamic load balancing. You'll end up with one overworked server while the others just sit there idle.
Plus, if that one server goes down, you lose all your user state. Real distributed rate limiting takes serious architectural thought, usually involving local memory caches syncing asynchronously with a Redis cluster so you don't lock up your main request path. Which brings us to part 4, handling HTTP 429s gracefully. We've built a defense. Now let's flip the perspective. How do we and our clients handle hitting these limits like actual professionals? Literally every major player in the industry enforces strict limits. GitHub has a hard cap of 5,000 requests an hour for authenticated users. Stripe enforces 100 requests a second per account. Google Maps sits at 50 per second. They are completely transparent about these numbers, and as API developers, we need our clients to handle hitting these exact limits without just totally crashing their applications. Which brings me to the absolute golden rule of API design. Use rate limit headers. Never, ever just silently reject traffic or drop the connection. You have to include HTTP headers in your responses that tell the client exactly how many requests they have left and exactly when that limit is going to reset. Don't just ghost your users when they accidentally send a bit too much traffic. Give them the data they need to slow themselves down. And on the flip side, if you are the one building the client that's consuming a restricted API, there is an exact 3-step process you have to code. 1. Constantly read those rate limit headers the server gives you. 2. Use those headers to proactively self-throttle your own app before you ever hit the wall. And 3, if you do get slapped with a 429 error, check the retry after header, politely wait that exact amount of time, and then retry gracefully. No endless while loops, no panic crashing, just smart, resilient code. So I want to leave you with this to think about before you go commit that new feature or launch that next product. Is your architecture truly designed to survive the next unexpected traffic spike? Rate limiting isn't just some annoying restriction, it is the absolute foundation of a reliable, mature system. So go review your endpoints, double-check your load balancers, and make sure those HTTP 429s are locked and loaded. Thanks for joining me on this explainer, and I'll catch you in the next one.